Good afternoon. Thanks for joining our webinar. My name is Yin from Rexel, and I'll be hosting the session today. We'll be starting shortly. We're just going to allow a little bit more time for the rest of the attendees to log in. Thank you for your patience, and we'll get going in a few moments. Hello everyone, and welcome to today's webinar with Schneider Electric on an introduction to UPS Uninterruptible Power Supply. My name is Yin, I'm the Marketing Executive at Rexel, and today I'm joined by Peter Stanmore, the Senior Solution Architect from the Secure Power Division of Schneider Electric. Just a couple of things to note before we do start, that this is a recorded webinar and it will be available to watch on demand on the Rexel website. This webinar is also CPD accredited, and the certificates will be sent directly to the email address you registered with for the webinar, which can take up to 4 to 5 weeks to arrive. If you have any questions throughout the session, please feel free to pop them into the Q&A bubble, which you can select from the menu on the side, and we will answer them at the very end. Now passing the time over to Peter.
Thanks very much for the introduction, Yin. Thank you. Good afternoon, everybody. Happy Friday. Thanks very much for joining me on this CPD webinar. As mentioned, Senior Solution Architect within the Secure Power Division of Schneider. So that means I look after racks, power, cooling elements, management, etc. Everything that's part of specifically a data center build. But yes, here today to run through this UPS system presentation. So I'll start, and we'll have answers, question and answer session at the end. Thanks very much. Sorry, it's frozen. There we are. Apologies for that. So yes, looking at the agenda that we have, we're going to be looking at the elements of reliable power, why it's required, UPS topologies, energy saving operating modes, system architecture and design, UPS system design configurations. Important part of UPS quite clearly is batteries and the technology behind that. Connectivity and remote monitoring, what does that give you? What does that enable you to do? And what are the advantages? And if we have time, we can go to a solution overview, but that's not part of this presentation. We'll cover the elements as I've suggested above. So first of all, reliable power. Quite clearly, why do we need it? If we look at the environments that we're using power in, so it's buildings where power is needed for residential and commercial elements, life safety type systems, so smoke extract fans, fire lifts, etc. Those are the sort of elements that we definitely need secure power for. We need also in healthcare. Here we're particular emphasis, obviously, of demand to save lives and that for health across the healthcare environment. Then, as we all know, data centers, and that's something we're all familiar with applications on our phones that use a data center environment somewhere in the world to provide us the data that we need. And those data centers are used not just for entertainment, but also for running large business environments, etc. Those areas of critical importance that they're available and operational. If we look on the industrial aspect, particularly mining, we need to run machinery for equipment and for trading. If we're looking at water and wastewater, clearly there's a requirement. We've heard all perhaps heard of stories where power failure has meant that there's been a flooding in a local area, that sort of thing. So clearly power is required to maintain systems and keep pumps operating, that sort of thing. It's essential for waste management and water environment. And of course, oil and gas. So your offshore platforms, how do we maintain that continuous supply of oil and gas? And also, clearly, the people are working in those environments as well, supporting that themselves. Those are important to understand that, you know, that's critical to the operation of those aspects. If we look at the power grid itself, if we look at the power grid in the UK, we go everywhere from the high voltage systems over here, right the way through to various substations and switching stations, right the way down to residential, industry, infrastructure, data centers and buildings, the sort of environments that I mentioned just now. Now that power path, there's a lot of kit, a lot of people, a lot of systems connected to that, which can all actually have an impact on the power that's being delivered from the grid right the way through to our endpoint. And ideally, in an ideal world, that distribution network will provide us with a perfect 400 volt for a 3-phase system or 230 volt sine wave at 50 hertz to run all these systems on the right hand side quite happily. But we know that that's not always the case. The issues we can have across that grid caused by the equipment that's connected to it could be voltage variations, also frequency variations. We have possible disturbances, so you don't actually have a change, but you have a sine wave that's not clear. We can also have micro outages, so those small blips that perhaps you and I wouldn't notice, but the equipment connected to it could notice that, and it could have an effect on that equipment. And of course, excuse me, the worst cases are long outages, where we actually lose the power completely. And what do we do during that system, during that time? So the consumer, obviously there's an effect on all the consumers, potential consumers on the right hand side. And also that kit that's all connected can cause harmonics and power factor issues and actually provide a reflection of those harmonics back to the grid, which is not what the grid needs and not what everybody else needs on that. So how do we support these environments? What we can do at our endpoint, we can provide UPSs. So we allow the network or the switching from HV to NV to come down to local LV systems. We can put that LV supply through a UPS, and that will assist to alleviate the effects of voltage spikes, under voltage and frequency fluctuations, and provide the UPS is there to provide reliable and safe power at an ideal perfect sine wave. With regard to the harmonics that I mentioned, harmonics and power factor issues reflected back onto the grid, the UPS will also assist with that and alleviate that. So again, any effects on the grid are minimized by installing this UPS. If we look at a typical UPS system, it has 3 main functions. Surge protection. So if we have a spike or a surge of power from the utility side down through our system, the UPS should be able to take account of a majority of that surge environment, that event. If we also then, what we're doing then clearly is we want to provide clean power to our equipment. So we're looking to smooth the input power, replicate the pure sine wave on the output so that our loads are quite happy and sitting there quite comfortably with no issues. And of course, as we mentioned, in worst cases that we actually have a backup, a loss of complete supply on our grid. We're waiting for the for the grid to switch its power supplies to alternative sources, which is what they do when in the event of a loss. This is where our battery backup provides that coverage during an outage and while the grid is reset or reconnected as need be. And of course, the other part is that we will often have, we could have a UPS. The additional, the additional resource is that we will have a generator. A generator will sit there. So we have a utility supply, but during the switching of the utility to the generator restart, what we'll actually have is, so we have an ATS that switches those supplies. The UPS will help support that switching. So the switch from utility to the generator will be covered by the UPS. So we're then back up and running. If we look at, if we look at UPS topologies, we cover these ones. So the UPS standard is IEC 62040-3, and that defines the following topologies. So we have standby or offline, which is the base level of support. We then have line interactive, a line interactive UPS, which is the next level of functionality, and we will go into some of these and explain that. We'll then go to full double conversion online, and double conversion online is your UPS that's supporting your main data center large equipment environments. And I'll show you how that's covered, what I mean by that. The important thing to think of is that we have, as we move up that scale, we have high levels of protection. We move up in power ratings, typically from a few kVA, it could be 1 or 2 kVA, right the way up to 1.5 megawatts or multiples of those in a large kVA supporting load for a large data center. And obviously that comes with a cost. Again, how we look at availability of that power supply, I'll cover those sort of costs and how that replicates through those systems. A simple standby power supply, UPS. The classification here is what we would call VFD. So that means the voltage and frequency is dependent upon the utility. Yes, so our main power comes in from the utility. We have some surge suppression, which I mentioned. That's one of the things we want to do and make sure that we capture those surges of power so they don't get through to our load. And we've got some simple filtering, but effectively your load is sitting here directly connected to this input source from the utility. The other thing it's doing, we are charging the batteries, charging the battery here to make sure that's ready and available so that in the event of failure of this supply, we have a transfer switching and we then pick up the battery. The battery will supply DC power through the inverter. The inverter will then supply the AC power to the load. The issue here is because it's low cost, low complexity, we have a transfer time. So we have a switching time here. So it's just something to be aware of that on these simple systems, the switching effectively, it can sometimes see that, but ideally in an ideal world, it won't do. I mentioned about rating, so we're at around up to 2 kVA, and that's going to be just your single phase UPS, particularly around perhaps household electronics, personal computers, so something that's sat under the desk, office equipment, that sort of thing. It's just your simple basic level of power support. If we go to the next one, so line interactive, we get a bit more complexity on this one. So this is what we call as voltage independent. So this means that our voltage supply from the grid, we actually provide the output source of the voltage through the inverter is independent of the utility supply because we're effectively reforming the output. So what we have is we do have a transfer. We have a medium cost per watt. It's high reliability, but it's only used in typically up to 5 kVA devices. And certainly again, single phase. So again, the UPS could be on your desk, underneath your desk, because it may actually also be used to in a rack to support servers, switches and routers. So we've moved from purely a desktop application to thinking about equipment located in racks in your data center, supporting the business, perhaps in a rack at the back of the office, which has its own dedicated UPS. We are, through this inverter, we are also charging the battery, and in the event of failure, we do have a transfer time. It's potentially reduced under this topology, but that then means that the battery then will then provide the power to the inverter and then continue to support the load. And the last one, not least, is the one that's probably most people have heard of, is double conversion online. This is the most complex because effectively voltage and frequency are independent of the utility supply, in that the voltage and frequency input is actually rectified to DC by the input rectifier, which charges the battery and supplies power to the inverter. That DC power is then reconfigured as an AC output to supply the load. So as long as the UPS is seeing and the voltage window will vary, the allowable voltage window will vary depending on the UPS and specification. But typically, if it's within this limit, the UPS can take account of these and work and still provide a smooth 400 volts, typically 400 volts, 50 hertz supply to the load within this tolerance. So we have a tolerance at the front end, and we're taking that down to 400 volts on the output of the UPS. The static switch is something now we introduce as part of this, because what it does, it acts as a fallback position. So if you have a problem with an overload condition or a fault perhaps on the output that the UPS does not feel that it can cope with, what it will do is try to transfer the load through the static bypass switch as a backstop, if you like. And it's a way of capturing the load to ensure that as much as possible the load is fully supported. This provides excellent voltage conditioning. There's effectively zero transfer time because the battery is always connected. We have this double conversion. This is our main path. You can parallel UPS in multiple outputs, and it's suitable for redundant designs as well. Rating up to, in a single unit, could be up to 1.5 MVA, could be bigger, but you can then parallel units to give you higher capacity. As we suggest, paralleling capability up to 4 MVA, some may be able to go higher. Typical applications here are data centers, commercial industrial world as well. So this is where we start to think about operating machinery, as we mentioned in some of the earlier slides, and other critical infrastructures. Somewhere that needs support from a UPS, a double conversion unit, should be able to provide the power required. An important thing is if we look at energy operating modes. If we look at a UPS, clearly there is an energy efficiency to a UPS. And what I've done is revealed that figure there. But so the amount of power into a UPS, if we think of a data center, through the double conversion mode, there is a loss of power. Each rectification and inverter stage, you lose some power because you are converting power from AC to DC, DC to AC. So what you have is an efficiency element, and that has to be considered in terms of how much does that efficiency cost you through effectively your inefficiency cost you. So you could have 100 kilowatt UPS, actually 96% operating, then you're going to have something like 105 kilowatts input required to provide your 100 kilowatts output. And at an assumed level, so this example that's been put by my colleague, if we have a 1 megawatt UPS, if we have a 1% efficiency improvement, assuming we go from 96 to 97, at 0.2 kilowatts per kilowatt hour over the hours per year, 8760 hours per year, we'll have a cost saving of approximately £17,000. That's because we've taken a UPS and we looked at its operation at 96%, we've actually raised that to 97%. How can we do that? This is what we said. This is our worst case, if you like. We say 95% plus on efficiency typically. Legacy systems will be nearer the 95. The latest systems are coming out now nearer 97 already. So we're already, because of designs of technology, we're already moving those efficiency levels they are already improving by themselves in a full double conversion, class 1, we call that operation. The other alternative, which became a bit of a, I won't say fad, but it's another way of doing it, is I mentioned about a static bypass switch. If we put all the power through a static bypass switch, we bypass the double conversion mode. So we're not converting that power and we're not converting at this stage. So we're going effectively straight through to the load. The thing is about that, we're not regulating the voltage or frequency. Sometimes we're not recharging the batteries. It depends on the exact design of the UPS. Sometimes it will be charging, sometimes it won't. There is a transfer issue because we actually when this line fails, the utility supply fails, the batteries to take over the load, we've got to start the inverter. So there's potentially a transfer time issue, and also the load is exposed to the harmonics and the power factor that may be coming down that utility supply directly to the load. If we look at an active eco mode, what we actually do is we run the inverter in parallel with that bypass supply, and that means that the inverter is ready and available, so that in the event of failure, effectively there's no transfer time. We've improved our efficiency up to 98%. In most cases, it's high 98 into 99. So it's getting very close to what is in eco mode, but we're providing additional levels of protection. We are also providing some harmonics, sorting out the harmonics down the line, and also providing some power factor correction back to the grid. No transfer. We're recharging the batteries so they're ready and available as soon as they come to operate. And whilst we're not regulating voltage and frequency, this bypass line will always be looking to make sure that is within tolerance. And if it's not within tolerance, it will switch straight away to battery with the inverter that's operational. So again, we have no transfer time. So potentially sometimes happens a difference between eco mode and active eco mode. The percentage difference is in fact you're paying for class 1 operation. And if we look at what happens, this is look at the curves on the sine wave output on eco mode. We have a disturbance potentially because as I say, we have a transfer time, and this is with the load directly connected to the utility supply. Our active mode means that, as you can see, the transfer when we have the failure is much smoother, and we can actually ride out that with no transfer and no risk to the load, because we actually are operating in a class 1 mode of operation, equivalent to our double conversion mode of operation. Looking at some of the elements of system architecture and design, we can have a standalone UPS, which could be fitted with so we'll have multiple standalone UPSs to provide a capacity of a system. So we could have 3 systems. A modular design, what we do is we take those power modules, put them into a single frame. They'll have a common battery rather than a separate battery, but we provide the modularity. So we have the ability to scale and understand and to scale up that system and resize it if need be. A standalone UPS, we take a 500 kilowatt UPS as our load is growing. We have at a later date, we have a second UPS, and that takes us up to 1 megawatt. We add another UPS, another demand, because the load is growing. So as long as the infrastructure is there, yes, you can add additional UPSs to provide that additional power output. But another way of looking at it is on a modular UPS, we could take a frame, and whether it's increase the capacity by adding a cabinet within that frame or part of that frame, or adding modules within there, we actually scale up So we've gone from a multiple UPS system to effectively a single UPS system with a single or dual input and a single output. But you can see we're scaling it up through the life cycle of the kit. And some of the more up-to-date, some of the UPSs are available with live swap of the power modules. So if you have an issue with the power module within the frame, that a trained operative can change that module themselves, which obviously it reduces your mean time to recovery of a system. Internal module redundancy. So we mentioned about, you see from the previous slides, we've scaled up. What if we actually look at the capacity of the system? We call it 1,000 kilowatts, so 1 megawatt system, because we have 250 kilowatt modules. Effectively, one of these is redundant. And what you'll find most of the time is, in most UPSs, all these will be operating and sharing the load. It's just that should one of the systems have a problem, an issue, it will drop off the bars or isolate itself, and the rest of the system can carry on operating. So whichever one of these is, you can provide that internal modular redundancy. It's another way of doing it rather than having a separate UPS to provide that functionality. Improving power availability. So where N is the amount of power required, I mentioned we can have 2 UPSs, N plus 1, so that's 2 UPSs operating in parallel. We can also have on a system, it could be operated as 2 Ns, so we have completely 2 separate power paths. 2 power paths providing power to our load. Quite clearly, a scale of availability is that N1 system, N plus 1 is 2. 2N system will have 2 independent power supplies as the main source. And 2N plus 1, we also have redundancy within that as well. Now that is the highest level of availability because we can use the plus 1 and we can even lose an N or any combination. And what happens, that means that we have the highest level of availability. If we look at the scale of cost, quite clearly, this is 1 UPS, this is 2 UPS. This is 2 UPSs across 2 systems, so 2 separate input boards, 2 separate output boards, and this one, 2N plus 2, again, the cost is the fact that we've got an N plus 1 in there somewhere on each side when we already have a 2N system. But if we actually look at the issue there, potentially, is the system efficiency. And we mentioned about the effect of efficiency on cost. So what you have here is you have the lowest system efficiency on the 2N plus 1 because you have so many redundant components. Your availability is potentially higher, but actually your system efficiency is lower. So again, that's why you're driving and looking at what I mentioned about efficiency of UPS and how best that and the topology used to support that. So this is what we were saying about a 2N system, a typical configuration. Apologies, they keep coming up. I thought I was logged out, but yes. So 2N. This is our 2N. Here's our load, 300 kilowatt load. It could be supported from N, and that's our A side and our B side. 2 independent systems, 2 UPSs on each. Then if we look at N plus 1. So this is where we have a UPS. We have a redundant UPS. We haven't had to repeat the whole system, but we have N plus 1 at UPS level. Clearly, yes, we have potentially single points of failure on the input board and output board, but usually often think of it that the UPS with its power components, it could potentially be the weakest link, but we have if we're using a modular UPS, we have ways of getting around that, so we can swap out modules quickly. So this is another way of looking at things if it suits the customer's specific application. N plus 1, high level availability. We've not oversized it because we have so we're covering if 1 UPS breaks down, we have the other is operational. Yes, there is as modern UPSs, these are both running at 50%, our efficiency is still going to be quite high. It's still going to be in the 90s typically. So that's one way of doing things. Disadvantage is that yes, they have to be the same design manufacturer. You can't just mix and match UPSs, same technology and configuration, because the output of these we need to be able to synchronize these outputs to support the load. And as I mentioned about potential single points of failure, but that's part of the assessment of the system. This is our worst case scenario or best case scenario, depending on which you're looking at it. This is where we had the 2n+1. So as you can see, we have 2n systems. Actually, we have on this one, we have a generator on each side through ATSs. n+1 is because we have n+1 on the UPSs on each side. We feed that power out to a PDU. In some instances, the customer load may have only a single input. And what they can do, they can run the power from each side through another ATS to supply your single load. But there's different ways of doing it. What we're showing here is the fact that we have two separate power paths. We have complete redundancy. So if you lose this whole side, any of these single points of failure cause a loss on this side, the other side will take over. But the other interesting thing here is that you can buzz couple here, even on the input side, so that it makes this power, or the generators available to either side in the event of something happening catastrophic downstream and you can't use it. Disadvantage, as we mentioned, is the amount of redundant components we have in this system. And therefore you do get some inefficiencies because they're not operating at best level of operation. And I mentioned about the 50% loading. That is because if you look at a typical modern UPS power curve, its efficiency is not at its highest at 100% load. It's at its highest down perhaps for 75, 50%, because we always know in our design of UPSs, rarely are they used sitting at 100%. Optimally, it could be around that middle mark, and therefore the design and it meets its peak in efficiency and performance at that middle line, that middle loading. Important thing is clearly battery technology. So if our UPS is there to capture a failure, cover an outage, what's the storage solution behind that? So we think of what I'm going to do is cover all this. So is two elements, VRLA and lithium ion. There are others on the market, but concentrated, those are the two we see as the two mainstream solutions. VRLA is tried and tested, they've been around for years. We can have, in modern UPSs, they're not all standalone batteries. What we call third-party batteries from known manufacturers that we configure. What we can use, a lot of UPSs would use a modular battery solution that is a bit like a plug-and-play system. We mentioned power modules in UPSs, being able to plug them in. Modular batteries in a similar way. A trained operative can scale those up and add those if need be. So this is what I said about a trained person. This issue, when we have classical batteries, a complete battery, classical battery, separate batteries, they all need interlinks to connect them to make the DC voltage required for the UPS. So you need trained people, all the safety equipment, etc., to install this classical battery. But on a modular battery, you don't, because the batteries are actually encased within these plug-in drawers and housings. But it is an option. You have modular, perhaps short run times, classical batteries for longer run times. How do we house those batteries? Typically on open stands for the classical batteries. Sometimes they're in separate battery rooms, and that will have an associated battery circuit breaker with it. And also, we can have a cladded battery stand. So we have a freestanding battery. Sometimes this sort of cabinet, it looks like it's got a classical battery in it, but it may be a modular battery within there. And there are different tunes on that we play with that to increase the runtime for the associated UPS requirement. So as I mentioned, cladded stands, open stands is one way. Modular batteries, sometimes on some UPSs, the first set of modular batteries are below the power modules within the UPS. When you need slightly longer runtime, you extend that into a subsequent cabinet. If we compare this to lithium-ion, lithium-ion is as an alternative, has been around for a number of years now. The benefits are, what we see are the fact that the number of cycles that you can cycle a lithium-ion battery from full charge to discharge to full charge to discharge over its lifetime could be up to 10 times the number of cycles. The expected life as well. Your VRLA, you may have a design life of 10 years, but actually they're all being swapped out between 5 and 8 years, depending on how they've been managed and monitored. The expected design life for your lithium-ion could be 2 or 3 times more than that. It has less weight. That's with big battery systems. That's always something about what's the floor loading, how can it be supported. It's less footprint. They're more compact. They are more compact. This is only, apologies, this is only a small picture, but you can see we have a number of batteries sat within a normal floor standing cabinet, and we'll have a number of those together supporting the UPS as need be. But certainly footprint is often a consideration. Higher operating temperatures. So what we say is here is that if you have issues with air conditioning within the room, a lithium-ion battery, it may, the higher temperature for an extended period may have an effect on the life of the battery. Yes, as it would do, as you'd expect. But fluctuations for momentary changes, it'll be less critical for the life of the lithium-ion battery. And that means it's predictable and manageable. We'll cover a little bit on the manageability in a moment. 4 times the shelf life. So unlike a VRLA, which you need to recharge every 6 months if it's on a storage condition, your lithium-ion battery could go into storage and could sit there, provided it's within the environment that we say that is suggested by the manufacturer. It will sit there for a certain amount of time. You won't need to pull it out and think about a way of recovering that battery, recharging the battery. The result of this expected design life, if we look at the TCO of the kit, so the total cost of ownership, we could expect perhaps 30 to 50% of savings, and that is primarily because if you look at lithium-ion battery, you may get 12 years. You could even get 15 years life expectancy. You might have changed your VRLA battery 2 or 3 times even before you need to consider what's going to happen down the road for the lithium-ion. Initial capex, this is an interesting one. So the initial capex as well, which was putting people off perhaps in the earlier days, we're saying now it's around 1.2 to 2 times. That's interesting because on this lithium-ion journey, say that I started to use these and configure these a number of years ago, that initial capex was around 2 to 3 times in effect. So that figure has come down with volume usage, more manufacturers using it, more usage in the UPS market, not just in the other markets that it's been used in. And we have a faster recharge time. So if we have a battery of a certain period of runtime, we know that with the UPS sitting behind it, the lithium-ion battery will take more of that recharge power with no effect on the battery, because on a VRLA you have to limit the recharge because the battery won't take it and it won't recover. But the lithium-ion battery, you can potentially recharge it up to 5 times. So you don't have a 8-hour recharge to 80%. It could be a lot less than that. It could be 1.5 to 2 hours, and it depends on the configuration. But that is certainly an element that can be taken in consideration. As far as lithium-ion safety levels are concerned, and that is something that is often spoken about. So first of all, certainly on the 3-phase systems, the lithium-ion manufacturer, it's a certain type of lithium-ion, a certain mix that is used, which is safer than provides a high level of safety. However, we then we put a BMS on the system, and manufacturers will put a BMS on the system to look at what's happening at cell level, what's happening at module level, what's happening at rack level, and system level, and then reporting back to the UPS for DC breaker tripping, which is what you normally expect with a battery. But all these elements are there to support what's happening and monitor what's happening within that critical battery cabinet. And that's outside of what the UPS is doing to understand what's happening with the voltage in the UPS within the battery. Last thing I think on this slide is, as we draw to an end, so if we look at connectivity remote monitoring, it's important that we have visibility on what's happening to the UPS. If we use this legacy car technology, so this guy who started his car back in 1900 whenever, how did he know it was running? Because he could smell it, and it was noisy. Modern days meant that we actually attached things like RPM, temperatures for the water temperature gauges. We understand what's happening to the engine in terms of RPM, oil pressure, that sort of thing. And as we know, new car technology, I mean, my own plug-in hybrid has far more menus and options in there than I care to look at. But at least if I want to know what's happening for fault finding, or if it goes back to the garage, they can look at what's happening. So it's a similar way. How do we manage our UPS? We can put in a number of cards in there to report out on whatever we want to do. So is it SNMP reporting, or is it Modbus technology because we're reporting back to a building management system? Either way, whether it's through our NOC or through individual pipeline into our UPS, we can understand what it's doing. So notifications, it sends you alarm. Data login, it tells you if there's a problem. Your FSR can then go to site and they go into a menu and understand. They go to the next level to understand what's happening if there's been a problem with the UPS. The user can actually see what the events were, what the status is of the UPS. So if an event happened or something like that, they can actually look through the event log and see when that timing took place. Things like firmware updates, you can do that through these cards. So you don't need to send an engineer to site necessarily. If it's connected in to your interface, obviously behind firewalls and things, and you have access to that, there are ways often ways of updating the firmware on the UPS remotely. And also the other thing that people use is a network shutdown. So your UPS has a certain capacity. If it has a failure, it will send a signal out to the management to actually start gracefully shutting down equipment, because often is the case, a graceful shutdown of IT equipment means that it can be started up much quicker than when there's been a dramatic shutdown and everything's dropped out together. It means you have to reconfigure on re-energizing. So it's important that we have capacity for UPS management, monitoring over customers' interface, third-party browsers, that sort of thing. It's available and in there. And I think that's enough from me. Thank you. Thanks for listening. If there's any questions in the chat in.
Thanks, Peter. We covered a lot of information there. So if you do have any questions or thoughts on the topic, then do share them via the speech bubble on screen. As Peter mentioned, we'll now have a Q&A time. There's 2 questions that we've got, so we'll go through those now. But yeah, as I said, feel free to add your questions and we can go through those. So the first one, can the UPS be used for long run times in a data center application?
So the answer to that is yes, you can run the IT for as long as you need, or as long as you feel that you need to maintain continuity because of cost. However, there are other things to consider, such as a server is effectively a heater sitting in a rack. It's uses a small amount of power for the IT. Because it's producing so much heat, if you're not supporting those other devices like cooling, that sort of thing, then sometimes a long runtime is not available to you. So you have to understand what the power path is and how the rest of that environment supporting the IT is actually supported and provided.
Thanks, Peter, for that answer to the question. And the second one, when would you use modular and when would you use an external third-party battery solution?
So this relates to my presentation. So what you have is if you look at a modular battery, will give you a finite level of runtime. Typically, a UPS, you'll have a number of modular battery cabinets that can connect to it, and that will give you a finite level of runtime. If you do need to extend the runtime, what you then may need to do is look at a classical battery cabinet where the UPS manufacturer will work with a third-party battery suppliers to provide a solution that has a certain number of certain size of battery, certain number of rows, certain number of blocks on it, etc., to meet a higher level of runtime that is not available through the limitations of the modular battery.
Thank you. Okay, I think that's it for questions. If there's no more, then I think we can wrap up here. Thank you, Peter, and thank you everyone for joining today. If any of you do think of a question afterwards, feel free to send them over to marketing@rexel.co.uk. As mentioned earlier, CPD certificates will be sent directly from CPD, which will take up to 4 to 5 weeks and land directly in your inbox. Thank you once again for your time, everyone, and we look forward to having you in our future webinars. Goodbye.
Thanks for joining. Thank you. Cheerio.